How's everybody doing? Get a chance to start on the lab? It's kind of a pain, so I would recommend starting sooner rather than later. There will be a little bit of work getting off the ground, so things that you might need to know or do is to import JUnit to your project. The slides on how to do that are in the second slide deck that are up on Canvas, so you can see how to do that, or you can Google it. You can also just kind of hover over any of the JUnit specific errors that you get. If you have something like an at test or an at before class or something of the sort, just put your mouse over it and you can select import JUnit from there. One other thing you'll need to think about is making a source folder, since there's no code associated with this project that's coming in. So you'll need to make sure that you make a source folder and identify it as the source folder for your project. If you have any questions about how to do any of that, see me in office hours, I'd be happy to help. Last time, we were in the middle of talking about the decorator pattern. We were coming up with an ordering system for a coffee shop. And we started out with some very bad ideas that we were in the process of figuring out how to improve. We ended up with a system that was going to decorate an object with some toppings or condiments. So we started with a dark roast object, and we decided that we could decorate or make an outer class for it that was a mocha object, and then make an outer class for that was a whip object. So we're creating this Russian doll style system where the outer doll is a topping and you open that up and hey, it's another topping. You open that up and hey, it's another topping, and you open that up and hey, it's a coffee object inside. So something kind of like that is what's going on here. So we talked about how to do it. We talked about how to call the cost method on this and what this looks like. It turns out that it's a recursive procedure that just calculates the cost of the current object and recurses and looks at the object that's inside of it, that it contains. And then you do that and the object that it contains until you end up with a base object. In this case, the dark roast object. You call the cost on that, you get an actual value, and then you just sum that back up the recursive chain of all of the objects that are decorating it, and that's the way that we're going to calculate the total cost. So we then looked at the full UML for the decorator class, so the decorator pattern that looked something like this. So we ended up with beverages. A beverage is an abstract class. We could have concrete classes that were the house blend or the dark roast or the espresso or the decaf. And we also had condiment decorators. We had an interface for that, and we overloaded that, or not overloaded, we implemented that with all of the different toppings. And now this is a much more extendable version of this code because we can add a beverage. And each of those beverages can still contain those same condiments, and we can add condiments, and each one of them can, they work with any of the beverages. One of the weaknesses that we had identified before was that we might like to be able to do something like restrict the kinds of condiments that exist on different beverages. And that's going to be a little bit more of a pain to implement. It's not really under the scope of the decorator design pattern, but it is certainly a weakness that should probably be addressed if we were going to design some kind of kiosk for an actual coffee shop. Questions on anything that we covered last time? All right, we're gonna take one more look at inheritance versus composition. So we see that there is still inheritance embedded in this system. One thing to note about decorators is they're going to end up having the exact same type as the objects that they are decorating. So a beverage decorator is a beverage object. So this is a little bit strange that the house blend with caramel and chocolate and a decaf with chocolate and whipping cream, both of those are beverage objects. But we're using inheritance to define our behavior. The behavior that we end up defining is just a composition of these decorator objects. So a decorator is composed of another decorator, is composed of another decorator, is composed of a base object. That's what ends up happening. So the benefits of this, we end up with flexibility. Any beverage base type can be decorated with any subset of condiments. This works really nicely if we want to allow the customer the ability to mix and match during runtime. We can decorate an object at runtime. We don't have to wait, we don't have to compile our program with the knowledge of what they're going to be decorating. It's something that can happen during the execution of our program. And that ends up being really important and necessary for things like any kind of always online system like a kiosk. We need to be able to specialize in runtime behavior so that we can make sure that it can be interacted with and it's able to handle that interaction at runtime. It's also extendable. We talked about how we can add new base drink types, new condiments, and none of those additions require us to go back and modify the existing code. So extendability is some flexibility here as well, which is good. And then, as I mentioned, we can define object behavior as the program is running. What that means is we can decorate objects during runtime. So let's dive into the actual code for this. Now that we have the actual idea of a decorator object, what would it look like to implement this code? No changes are necessary in the beverage superclass. Nothing changed about that superclass. So it is still going to look like this. It is an abstract class. What about this code tells us that it's an abstract class? The word abstract, that is, yeah. If we analyze anything that's not the name, how do we know from the internal descriptions of the class that this is abstract? Beyond the abstract. But yeah, we don't have a constructor. We can't make a beverage from this, but cost is not implemented. And that's because if we just have a generic beverage, we don't know what a beverage is going to cost. When someone walks up to the kiosk, before they've placed their order, we don't know what base object they're going to order. We don't know what condiments or toppings they're going to order. We don't know what the cost of their beverage is going to be. So at the beverage level of abstraction, we can't define even a process for the cost because we don't know how many condiments there are going to be. Because of that, it needs to be abstract so that in the concrete classes, we can talk about if you add this condiment, here's how it affects the cost. If you order this base drink, here's the base cost of that drink.
So would there be any reason to ever populate this cost? Or
If every drink costs the same?
Well, what about if you had a defined, like, let's call it a tax or something?
Okay, so like a tax that.
Would you define it here or would you still define it?
If it's always the same, no matter what, you would define it at the highest level that you can. Whenever, I like to think of whether or not there is ambiguity. So if I asked all of you to draw a beverage, if there was no way anyone could draw something that was different from somebody else, then you would have the description or the visual of what that is defined in the base class. If all drinks cost the same, if I asked, if you all ordered whatever drink you wanted, if there was no way for it to possibly cost some other value, then we should define the cost function in the highest level that you can in the superclass. But encapsulating what varies is one of those object-oriented techniques that we talked about. So encapsulate what varies inside of the subclass objects rather than at the abstract level. The abstract class for condiments is very straightforward. It's abstract. It doesn't define the get description because each condiment is going to have a different description. Let's take a look at the base beverages. So here is an example of what espresso looks like. Let's just zoom in on that for a second. So it has a constructor because we can actually make an espresso. Note that we could not make a beverage. Why not? Why wouldn't it make sense to have a constructor in the abstract superclass beverage? We can't instantiate it. Yeah, we don't know the shape of a beverage. We don't know what it contains. So there's no way that we can construct that object. Maybe if the constructor were a part of another constructor, we could abstract part of a constructor into the base class that gets called as part of it, which is what you see when you use the keyword super in the constructor of a child object. So you can have a constructor, but you need to be able to make one of those base objects. And to make a beverage, we don't have the information to do it, so we can't write a constructor for it. Whereas an espresso, all we have to do to make an espresso object is to define the description. So the description of an espresso is just the word espresso, as far as we're concerned here. So then we have a base cost of an espresso with no toppings, no condiments, as somehow $1.99. Man, those were the days. Note that we also have the extend beverage because an espresso is a beverage. So we have that is a relationship between the child class and the parent class. House blend just has house blend coffee, and the cost of a house blend is somehow only 89 cents. So all we have to do is set the description in a constructor, make sure we extend beverage, and define the base cost of that object with no decoration. No toppings, no condiments, anything else. Questions about either of these classes? You'll find as you write bigger and bigger projects that the classes that you write get smaller and smaller. These classes are tiny. They don't do very much by themselves, but they do a lot more in tandem with each other. So the different decorator classes. Here is the condiment decorator. So a condiment decorator is composed of a beverage. Does that make sense? That the beverage is the internal object of the condiment decorator. So a mocha in this case, the internal object could be something like a house blend. And a house blend would be the object which we have decorated with chocolate. So this would be a house blend with chocolate. We need a constructor. The constructor must take a beverage because we cannot have a mocha object without a beverage. We must apply that chocolate to something. We can't just order a mocha with no coffee. That's a chocolate bar. That's a different object from this completely. So it requires that we have a beverage in the constructor. And then we set the field of the beverage, whatever the object inside of this is, with that object. But note that this beverage could also be another condiment type. So we could have a mocha that's decorating a whip, that's decorating a house blend, something like that. The description is going to access the description of whatever it is decorating. And then it's going to add comma mocha at the end. So if the internal object here were a house blend, the description would now be house blend, comma mocha, which would tell us now that we've decorated the house blend with chocolate. The cost function is going to be defined in terms of the cost of the beverage that it's decorating. So adding chocolate to a drink is going to add 20 cents to its cost. Whatever it is decorating, a house blend was 89 cents, and espresso was $1.99. Those are very different costs, but a mocha can decorate either one of those objects. So depending on what the value of the beverage type of the field is, that will change the associated cost of the entire object. But we don't define that in the mocha class. We define that as some process of querying the cost of the internal beverage and adding the cost of the chocolate to it. Does that make sense? Questions on why this code is structured the way that it is so far? So how do we use it? We want some kind of driver class for this. Here's an example of how we could interact with all of the classes that we have written now. So here is a driver class with a main. We are going to make a beverage. Note that we're using polymorphism here, defining it just as a beverage. When we instantiate it, we say new espresso. So now we have a beverage that's really an espresso. Totally allowed to do this. This is just polymorphism. So we can print the beverage's description, and we can print the beverage's cost. This is just the base beverage. Great. That's an espresso with no decoration. Beverage 2 is a dark roast object. It's still a beverage. Note that that's using the same base class. That's perfectly fine. We can then add constructors to this. Note how we say beverage 2, we're redefining beverage 2 equals new mocha, equals new mocha, equals new whip. We're not making new objects, we're just adding, decorating the constructor for that without redefining it as a new object. So beverage 2, draw this out a little bit because this is fun. We start out with just a dark roast object, and beverage 2 points at this object that is a dark roast object. When we say beverage 2 equals new mocha, what we're doing, if we look back at the mocha constructor, that wasn't actually making a new object, it was taking an object, a beverage, as a parameter. So what this is really doing is we're now adding a circle around this that is a mocha object, and beverage 2 now points at the mocha object. Inside of that, there is a field that is the dark roast object. When we say beverage 2 equals new mocha, we're again passing it in, and as a field, we're going to pass in this mocha object that's decorating this dark roast object. So that we make another circle outside of this, that's another mocha, and beverage 2 now points at that object. We're redefining beverage 2 to point at the new mocha that's decorating the old mocha that's decorating the dark roast object. We do exactly the same thing with a whip. We make one more decoration. We're going to surround this entire object with a whip object, and now beverage 2 is going to point at that object. Now, if we were to call beverage 2 dot get description, we would see that this would be a recursive procedure that would go down, 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 down to the base case that is the dark roast. We would print out dark roast. And then we saw that there was comma mocha. So as we go back up the recursive chain, we're going to append to this dark roast, comma mocha. Back up the recursive chain, append comma mocha. Back up the recursive chain, comma whip. And this would be the description that gets passed along to the barista who's going to make this object for you.
That's a lot of mochas.
Someone really likes chocolate.
Fair.
Can't really blame them. Does that make sense, how the description is being put together recursively? How we're starting with the base object, and then as we go back up the recursive chain, we're just appending more string, appending more string, appending more string, and then finally returning the entire string object that represents the description of the drink. How does the cost work? When we query beverage2.cost. Yeah,
Getting it from the separate beverages, is it like already defined in those?
it's defined within the mocha class, it's defined within the whip class, but the entirety of this object is going to be, basically, if we wanted to write this as an expression, the whip says that, all right, we're gonna assume that the whip is also 20 cents, same cost as the mocha. So we would say that the first thing we would query is, all right, the whip is going to be, what is the cost of this whip object? The whip object is 20 cents plus something. Whatever the cost of this internal object happens to be. So we're going to go down a recursive call that says that, all right, we're gonna pass down this 0.2. And we're gonna try to answer this question mark. So what is the cost of this mocha object? This mocha object is 0.2 plus something because it's composed of something. So now we're gonna query this mocha object, which is gonna say that that cost is 0.2 plus it has a base object, so we don't know what its cost is going to be. We're going to query its internal object, and we're going to see that it's a dark roast object that actually has a cost. It's not an expression, it's just a straight constant. So this is going to be 0.89, the 89 cents for the dark roast object. Now we can go back up the chain and replace this question mark with 0.89. We can go back up the recursive chain and replace this question mark with 0.2 plus 0.89. So this question mark is now 1.09. We can now go back up the recursive chain and replace this question mark with 0.2 plus 1.09. So this is now 1.29. And what goes back for the entire cost of the object is 1.49. Does that make sense? Questions about that? If we look back at the code, we will see exactly how that was defined in the code. That each time we had an expression, and that expression involved an unknown. That's because that unknown was the field that was the beverage. And unless we have an object that is an exact beverage type, like a dark roast, then we're not going to know what that cost is yet. We have to continue to query what is the object that is inside of your Russian doll, and what's the next Russian doll, and what's the next Russian doll. So that is a decorator. Of course, it's not a design pattern unless we can talk about the cons that are associated with it. Again, if this was just something that you should always use without questioning it, then we would teach it to you earlier. Imagine that the manager of this coffee store says, sometimes I have sales and I want to get rid of my house blend stock because it's getting old and near its expiration. So I need to mark it off so that I get more customers. All house blend orders, regardless of what toppings you have on it, are all 30% off. How could we do that with this system?
would you only change the cost of house blends?
Yeah, we'd have to have,
The only house blends with the cost change.
the issue with decorators is once we decorate it, we don't know what the base object is anymore. We see a mocha object or a whip object. We don't see a house blend object or a dark roast object. So there's no way for us to know once the order is placed without analyzing the description string. We'd have to go print the description and parse that string for something like, does it contain house blend? So we need to modify our design to account for this. The decorator object, the design pattern does not help with this at all. We need to use other tools in order to be able to incorporate that functionality. Also note that when you're making a copy object, it happened in the client code. If we go back and look at the last piece of code that we looked at, the decoration here is happening in our driver. It's not happening in our object's construction, which means that it's the client's responsibility to do that decorating. That's a problem if you have a client who doesn't know what they're doing. So as we see frequently with design patterns, you need to solve some of the issues that are present with one design pattern with another design pattern, and this can lead to a long chain of applications of design patterns. So this can be solved absolutely with a creational pattern, either builder or factory. Either one of those would solve this issue, but you have to know about it and you have to solve this issue that is created by using the decorator. So we will see that patterns like builder and factory have the ability to create decorators during their construction. And then they manage the encapsulation so that a user can't hack in and create a drink that has free toppings, or that they don't have any control over the associated logic of how this is happening. We also see that with our printing, we find that if you want extra chocolate or extra shots, that it's going to print repetitively. So additional logic is going to be needed to do things like replace certain strings, substrings with other substrings. You may want to replace extra shot with triple shot, or mocha with something that represents chocolate lover, or something of the sort. So you can imagine if get description didn't return a string and instead returned an array list, you could then look at the elements of the array list and try to parse for that. Think how difficult it would be to do this with just a string object, because you don't know the order of the decoration. The client could say, decorate my dark roast with a mocha and then a whip and then a mocha. And you'd have to be looking for all of the times that the mocha substring appears in that, because you don't know exactly the order that it would be in. So the logic that you would find would have to be very robust for that. And using a list would make that significantly easier. One other con that we've seen here is that the condiment classes and the coffee classes were all very small. There was a constructor and a description, and that was the entirety of the object. So what you'll see from a class design perspective is you'll see lots and lots of classes in packages with lots and lots of packages in your project. And if you look at any one of those classes, you find that there is very little code in those classes. So that's just one of the, what we accept when we adopt the pattern. A decorator will indeed create lots of classes with very little content. Last thing I want to show you with regards to decorators is that these are frequently used in practice, even within the Java API. So for instance, has anyone used a file input stream before? Probably. You use this frequently when you're reading from a file. So a file input stream is an object that has certain functionality and can be decorated with a buffered input stream or a line number input stream that allows you to do things like read in starting at a particular line number instead of just at the start of a file. If you just use a file input stream, you start at the very beginning of the file. But if you decorate your file input stream with the ability to search and buffer it, meaning that you can move its position, and then a line number input stream that's capable of knowing when lines start, you add functionality to your file input stream to be able to do more complicated things with your files. And if you look at the actual UML for input streams, you can see that the abstract input stream, we have abstract decorators, file input stream, string buffer input stream, byte array input stream, and filter input stream. And each one of those have concrete decorators, pushback input stream, buffered input stream, data input stream, and line number input stream. So in practice, we have this huge system for handling files and input in files that is itself a large system of just decorators. And then you can use this and decorate your own file input objects to be able to have the functionality that you desire or you need for your application. So you get a lot of power by, you can add a lot of power to base objects by using the decorator pattern. Again, should not always be used, but when it is appropriate to apply, it can be very powerful. That's all I have to tell you about decorators. Does anyone have any questions about the concept before I assign you a lab eventually about it? Right. We'll move on to the next piece of fun that we are going to talk about, which is code smells. Code smells are very fun. This lecture will probably not be. Basically, this is going to be a huge dump of lots of ways that you can write code that are not good. And I'll do my best to describe why each of these are not good and what you can do instead. But it's worth taking note of just how many of these there are, and also note, do I ever do these? What could I do instead? And I think that will help you to be able to iterate on the process you go through when you are writing code. So tell me if this sounds familiar. The night before a programming assignment is due. You've been working on it for a bunch of hours, and you have finally everything working to the specification. But, of course, you've been working for hours. So as you've been working for hours, the process of getting to the point where it's working to the specification isn't pretty. That process involved taking some shortcuts. And now that it's working to specification, you go back and you look at your code, and you're just like, this is a coding nightmare. It works, but I'm not proud of what I've created. And it's such a jumbled mess that I'm really scared that if I go back and tweak it to try to make it look better, that I might break something. So I'm just not going to touch it. Does that sound familiar? So this is what happens when we fail to apply solid design principles and go through the appropriate steps to write a program. Eventually, the code that you write for these classes, you want to add to your code portfolio. You want to be so confident in your code and so proud of it that you will show it to a prospective employer and say, I am proud of this. Not, I was working on this an hour before it was due, and I know it's ugly, but it works. So common ways our code can sync up the room, common ways that if you were to take a look at someone's code, you could critically analyze it and say, they could have done better here. So if you learn to recognize common code stink, then when you go to write your code, it will work faster. And it will look so much better. You don't have to go back when you're ready to be hired into a position and fix code that you haven't touched in years to try to make it look acceptable to a prospective employer. So I find that it's very worth learning about and learning to implement the better ways than these smells. So they're going to come in a bunch of different categories. There are 5 broad categories that have about 5 to 8 smells each. So we're going to be going through a lot of code smells, a lot of them. The first one is bloat. This is what happens when your code is just straight up larger than it needs to be. Over time, you get more and more and more code to do the same basic thing. We have object-oriented abuse. We have lots of object-oriented principles. If you fail to abide by those object-oriented principles when you should abide by them, then we end up with code that looks like it wasn't written in an object-oriented language. It doesn't handle or deal with the pros of object-oriented languages. Change prevention is a kind of smell that says that when you later want to go back and extend your code so that it does a little bit more or operates on new objects, you can't change it easily. You have to make large-scale modifications to your code that may break it. We have dispensables, which is just completely pointless or unnecessary code that with small amounts of refactoring, you can just take out of your code. So it's not quite bloat, but it's something that you can just straight up delete. And finally, we have couplers. And couplers mean that classes aren't communicating correctly, or they're communicating way too closely. You have 2 objects that don't really they shouldn't be having much to do with each other, and they're so coupled that you can't change one without changing the other, even though they don't really have much in common, or that shouldn't necessarily be the case. So even though these are broad categories, there's some overlap between them, like couplers and change prevention kind of go hand in hand, where if you have objects that are too tightly coupled, that might prevent you from doing some change. If you need to change one of these objects and you can't change it without changing the other one, even though the change has nothing to do with that object. So couplers and change prevention go kind of hand in hand. Dispensables and bloat kind of go hand in hand. But let's start talking about some of these code smells. Some of these are going to sound really familiar, and it's probably going to sound like a personal attack. I apologize in advance. First one, it's a design that is really gross, long methods. So bloat number 1, long methods. As you're decomposing a problem, it's really tempting to just start from main. And maybe you write all of the logic and then eventually you find, all right, I guess I'm just done. I didn't really think about the need for extra methods. And maybe there's some duplicate code in here, but the code is just one big, long logical block. As we go back to code, we don't tend to factor out code when we go back to it. We tend to extend the existing code. We add logic to methods that already exist rather than make new methods. As you do this over and over and over again, you end up with methods where design-wise, methods are supposed to do a single thing. But you may find that your method does 5 things or 10 things. And if later on, for instance, we wanted to extend this code to do something else, where in this 5-step process, we want to do the first 3 steps, but then branch it into something new, we can't do that because we have tightly coupled all 5 of these logical steps together in a single method. Whereas if we decomposed it better, we could call method 1, method 2, method 3, and then branch and do something else. So figuring out what goes in a method and keeping your methods short and doing a single thing is very important. So can prevent future extension, can prevent code reuse. You'll find that you have a lot of code duplication whenever you have obscenely long methods. So one possible treatment, you'll find yourself looking over your code and thinking, wow, I really need to write some comments in here because I don't even know what this code is doing. If you find yourself saying that, that means you need more methods. Each method should be doing something that is so short and simple that it doesn't need additional documentation. It only needs that Java doc comment that's at the top of the method. A 1-sentence description of what this method does. If your method needs more than that 1-sentence description, it's more than one method in disguise. If you find that and it's due to your method naming or your variable naming, it's worth making sure that all of your variables and methods have names that are very descriptive. Again, you should not find the need to comment in the middle of a method. If you do, your method is too abstract in terms of its naming, or it's doing too much.
What does intro method comments mean? Does that mean like inside the comment or inside the method?
They're usually bad. That's the very first thing you're taught is comment your code. And that is to make you think strategically, logically, procedurally about what every line of your code does. As you become more of an expert at programming, you're going to want to stop doing that. You're going to want to start factoring all of that out into one comment ahead of each method, and each method should be describable within a single sentence, because you are going to be writing code that other programmers are going to be reading. These aren't other 210 students who don't know how to read code. These are other people who read code like we read English. So if you have something that is descriptive and short, then it's like a 1 or 2 sentence summary in English. You can hand that to just about anybody and they can understand it. If you have very long conditional statements, if this, else if that, else if that, else if that, turn it into a method that returns a Boolean, true or false. The next one is large classes. It's very tempting, especially coming out of 210 and 211, to write all of your logic for a large project in a single class. And we will find that as in this class, the project that you write will have 20 classes in it. A lot of what you will submit for labs in this class will have lots of classes in them. So long classes, you can tell it's long if it has a bunch of fields, if it has a bunch of methods. If it's just hundreds and hundreds and hundreds of lines of code, it may be, not always, sometimes classes are this long, but it's worth considering refactoring that into multiple classes. Especially as you iterate over and over, you will find that as the requirements of your project grow, some of your classes are going to really start growing. So as you see this class that's getting really long, you should start thinking, is this really multiple classes? Can I split this logic into multiple different objects? It definitely feels better to put things into one object, but then using that object becomes a lot more difficult. It creates future headaches, you end up with duplicate code, duplicate functionality, and then you have one object that does 20 things, so you have difficulty uncoupling them. If you have another object that interacts with one of these 20 things, then you have this really large class that is coupled to this object that really only needs a small piece of that functionality. And it would be much easier if you could couple it just to the logic that it needs to couple, rather than being coupled to the entirety of the long class. So some tips. If you have a large class and you can think of making multiple objects out of it, it's frequently worth doing that. If you have a feature that can be implemented in one of many ways, or it's only used very rarely, you can use an inheritance hierarchy and split out subclasses from this. And that turns each of those classes into a much smaller class, and also creates a hierarchy that will be more extendable and more reusable, because then you have a superclass. So if we have lots of duplicate code in between a bunch of different pieces of this object, and you split this into an inheritance hierarchy, you can abstract all of that duplicate code up into the superclass, and you only have to write it once. I think we have time for one more. This one's a fun one. If you are very used to using primitives, ints, doubles, chars, you can kind of even think of strings. Strings are primitives in some languages. If you have an adversity to making very small objects, we can find that those objects are very useful. So something like a currency object that really just stores a single double value that represents that. You can add as a toString, whenever you print a currency object, the $sign just goes in front of it. And then you no longer have to worry about concatenating a $sign to a double wherever you want to print a currency value. So factoring that out into its own object can minimize the code reuse from just thinking about everywhere I print currency, I need to think about how to print that currency. That says that it should all be done in one place in a very small currency class. A range is another example of this, where you have a lower bound and an upper bound for something. You can make a range class that has a lower bound and an upper bound, and then rather than storing that as a primitive, you store that as a small object. Another example would be something like a phone number. You could store the phone number as an int, but since phone numbers get printed in a certain way, maybe it has parentheses around the area code, maybe it has a dash or doesn't. You can define different ways to print the same phone number, and you just store it as an object that has that primitive inside of it. So rather than just using a primitive, it might be worth making a class and then using that class wherever you want to use that primitive. So all of these could be stored as primitives. But you will find that you end up with things like floating point arithmetic errors if you have an integer and you always have to worry about dividing by 0, for instance. You could write a single divide by zero logic that works with your object, and then wherever you use the object, you don't have to duplicate or check, is it 0? Is it 0? Is it 0? Is it 0? It would be embedded in that object. You'll find that sometimes you can't extend it into the future without refactoring of some kind. What is also considered primitive obsession if you overuse static class constants. So if you find yourself doing like a public static final int a equals this, public static final int b equals that, and you have 5 or 6 of those in a particular class, think about, can that be represented as an object with a bunch of different possible values, or an enum, rather than having a bunch of static constants. So I think we're going to stop here for now. We're going to continue going over these. There are lots of them to come. It will take probably at least the rest of this week, But my goal on Friday at least is to have a practice problem that relates to reading from and writing to files. Because that is one of the important 8 skills that we should have ahead of next week's 8. So that's the plan for the rest of this week. Work on your strategy lab, and I will assign a decorator lab soonish, probably not today. You need to import it into your project.
Yeah.
Yeah, yeah, it's in the second slide deck, unit testing, and then I can also help with that if you end up with issues.
And then you can sure there's no sort of.
Correct.
So
There is no-
That's what I thought, when I was looking through it, I couldn't find it, so.
Yeah.
It's just.
Just double checking through, so I have the exam due tomorrow for
Yes.
11 to 12, or just like looking at that, so,
Yep, that